Hi class, welcome back for another lesson. Today's lesson is part 2 of static, which if we're going to look at equilibrium of rigid bodies. Now the learning outcome for today's lesson is to define torque and to state the condition for the equilibrium of rigid body, and then we're going to learn how to sketch and label the forces and solve problem involving forces in equilibrium. Now, in physics, a rigid body is also known as a rigid object, is a solid body in which deformation is zero or so small that it can be neglected. Now, before we move on to the equilibrium of a rigid body, let's learn of another quantity which is called as torque. I know you are familiar with the word torque when you studied on the chapter of circular motion. In physics and mechanics, torque is the rotational equivalent of linear force. It is also referred to as the moment of force, rotational force or turning effect. Just as a linear force is a push or a pull, a torque can be thought of as a twist to an object around a specific axis. Another definition of the torque is that the product of the magnitude of the force, and the perpendicular distance of the linear line of action of a force from the axis of rotation. The symbol of torque is called as tau. Now is the second concept we're going to look at. Okay, if a force, there's two diagram here class. The first diagram is we can see a force acts through the center of mass. Okay, the force acts through the center of mass, and the second diagram is the force does not act through the center of mass. Okay, so the concept is if a force acts on a rigid body. Now a force, when it acts on a rigid body, it can cause an acceleration. It can cause an acceleration. If the force acts on a rigid body, pass through the center of mass, which acts through the center of mass, not pass through, acts through the center of mass, will make the object to move in a straight line with an acceleration A. Okay, so if I want to make this object to be in static equilibrium, what must I do? A has to be 0. A has to be 0. That means F equals to MA. So F, which is the resultant force, has to be 0. Okay, so that means no resultant force acts on the body. No resultant force acts on the body. Okay, no resultant force acts on the body. But if the force passes through or doesn't go through or doesn't pass through the center of mass but anywhere around the rigid body, okay, the rigid body will experience two motion. The rigid body will experience how many motion? Two motion. Okay, the first motion will be a straight linear motion. Okay, which I'm going to write here, linear motion, or we call it as a translation motion. Okay, we can call it as a linear, we also can call it as a translation. So I'm going to just write here linear motion. Okay, Alright, the next one, it will linear motion will experience two motion. One is linear motion with an acceleration a. That means the object will move in a straight line with an acceleration a. Okay, the next one it will experience rotational motion with an angular acceleration alpha. Symbol is alpha. Angular acceleration symbol is alpha. So that means this is alpha. So that means the object will move also in a rotational motion, and it will go straight line like this. You see, the object will rotate and move in the straight line. Okay, so in order to make the object to be in static equilibrium, we want to make the object what? In static equilibrium. What we must do? We must make sure that the acceleration is 0 and the angular acceleration experienced by the due to the rotational motion, we must make sure the moment of forces is 0. So that means in order to do that, we have to make sure what? The first thing we have to make sure what? No resultant forces. Okay, in order to make the acceleration a 0, so no resultant forces. Okay, to make this motion the forces balanced. Okay, and also we have to balance the moment of forces in this motion. So no resultant torque. One is to balance this, another one is to balance this. So once it is both is no resultant forces and no resultant torque, then therefore no A, no alpha, that means this object will be in static equilibrium. Okay? Alright, thank you.
Condition for the equilibrium of rigid body. Two conditions are necessary for the equilibrium of rigid body. Condition number 1. There is no resultant force on the rigid body. Condition number 2. There is no resultant torque on the rigid body. Condition number 1 implies that the sum of the component of the forces along any direction is 0. Condition number 2 implies that when we take moment about any axis, the sum of clockwise moment is equals to the sum of anti-clockwise moment. Both condition 1 and 2 are necessary for the equilibrium of rigid body.
Look at how we can apply the concept of equilibrium of the rigid body in this example. So the most important thing when you read the question, you must know how to apply the concept. Okay, so here we have the following figure shows a uniform body of uniform rod of length 0.80. Okay, length is what? 0.80. So we have the length is 0.80 and mass 0.5 kg. So this is the first mass. We are looking at the first mass. Okay, resting, another keyword is resting. Okay, so let's look at the word resting. Okay, resting means tells us that it is in equilibrium. Okay, on support. Okay, another word there, on support. at NA, support at NA and at a point P, 0.20 meter from NB, 0.20 meter from NB, a load, that means we have another mass, mass number 2, a load, we have two mass, mass number 2 of 2 kg is placed at Q. Okay, I'm going to just write here load of 2.0 kg is placed at Q. So that means there is a mass here of 2 kg. Okay, from 0.20 meter from A. Find the reaction. Now they want us to find the reaction at A and P. The question asks us to find what? The reaction at A and P. Okay, so now what we must do is, so I'm going to draw this separately. So first thing, before I draw it separately, what we must do is we must draw the forces that acts on this rod. Okay, so here we can know there are actually 4 forces. Alright, so when you see the word support, support means it is supported by a pivot. Okay, so that means we say the word pivoted. That means there is a reaction force. Okay, so there's a reaction here. Support, there's a reaction here, which I'm going to label here as R1. Because why? There is a word support at NA and at this point here and at this point P here. So that means there is also another reaction here, which is, I'm going to label it as R2. Okay, then I know there's 2 mass. So when there's a 2 mass, there is also weight. The first weight will act directly downward, okay, which I'm going to draw here, act directly downward. So I'm going to write there weight. W equals to mg, m is 2, so I'm going to label it as 2g. Another weight is the weight of the rod, okay, which will be definitely in the center here, of the center of mass. So here it will be W equals to mg, so m is 0.5 g. So I've already drawn the forces. Okay, so first thing what we do, number 1, I'm going to write here, number 1, draw the forces that acts on the rod. Okay, all right, once we have finished that, I'm going to separately draw that. Okay, I'm going to just separately draw it, okay, so that we don't get it confused. All right, so it's like this. Okay, so we have here R1, okay, and then we have here 2G, and then we have it somewhere here in the center is 0.5G, and then somewhere here we have it R2. Okay, so I'm going to draw like this. Alright, so now I'm going to put in the distance. Okay, so here the distance here, okay, from R1 to 2G, this one will be 0.2 meter. Okay, so from here to here is 0.8, so definitely from here to here is 0.4, so this to this will be 0.2. okay, since here and here is 0.2, so definitely this one to this one is 0.2, because from here to here is 0.4. okay, done. Now I apply the condition of the equilibrium on of a rigid body in this question. Okay, what is the condition? Condition number 1. Condition number 1. What does condition number 1 says? No resultant force. No resultant force on the rigid body. Okay, so I apply condition 1. So I must total up the force. So the forces upward is equals to the forces downward. So R1 plus R2 is equals to 2G plus 0.5G. So R1 plus R2 is equals to 2.5G. Okay, alright, so this is equation number 1. Okay, then what I do, I apply now the second condition, condition number 2. What is condition number 2? No resultant torque. No resultant torque on the rigid body. That means the sum of clockwise moment, okay, moment of forces or moment, is equals to the sum of anti-clockwise moment of forces or moment. Okay, either one. Moments of forces. Okay, so now in order to apply this, the condition number 2, sum of clockwise moment of forces equals to sum of clockwise moment of anti-clockwise moment of forces. In order to apply that, so I'm going to teach you how to do it. Now first thing, you have to take a moment. Okay, what you have to do is you have to take moment. Step number 1 for under this, yeah, step number 1 under condition this, what you do, you take moment. You can take moment at any point. Moment means is force, so you can take moment at any point. You can take moment at R1, you can take here, you can take here, you can take here. Okay, that means you are setting an axis. Okay, so take moment. So I'm going to take moment about point A. So I'm going to write here, take moment about point A. Okay, so I'm going to draw here. I've already taken a moment about point A, so I'm going to draw I'm just going to simply just draw here, simply like that. Okay, it's not that you have to draw it, but just to let you all see that I'm taking moment from here. Okay, so I'm going to put my ruler here. Okay, so now when I'm doing that, okay, so you see when I'm doing that, there are 3 moments, there are 3 forces to be considered. That means 3 moments. The first moment, second moment, third moment. This moment, which is R1, is not considered. Because why? Moment is what? Moment is force times radius. And if I take at this particular point as moment, then the radius is 0. So automatically you no need to consider R1 into the equation, okay, or into the expression. So I just put it like this. Okay, so now I have 3 forces that I have to take moment. Okay, so if I now want to determine which one is clockwise, which one is anti-clockwise, correct? So what I do, okay, first, if this thing is supposed to rotate, in which direction will it rotate? It will follow the direction of the force. So the force is here. So it will definitely follow, wait, I'm going to just take a pen, different color. It will definitely follow the direction of the force, which is in this direction. So if the force is in this direction, it definitely will follow in this direction. So if the force is in this direction, it will definitely follow in that direction, towards the moment. You see, all heading towards the moment. Okay, so it's like that. If I take moment here, then the direction all will change towards the place where I'm taking the moment. Can you see? When I'm taking the moment, I put my ruler here, everything is towards, okay, is towards the place I'm taking my moment. Okay, so from here I can know this is clockwise, this is clockwise, this is anti-clockwise. Okay, so take moment about point A. So the thing is, I have to find sum of moment clockwise is what? Sum of moment clockwise. Okay, moment means force time. So clockwise I have 2. So is force. Okay, the force is what? 2g times with r. Times with r. R is what? Okay, the place I take moment, the distance of this force towards perpendicular distance. So you see, like wait, let me take another color pen. The moment will be the force which is this, and the perpendicular distance. So it is 90 degrees. So perpendicular distance from this to this is 0.2. So I put 0.2. Okay, then the next one is this and this. So I'm going to take another color pen. Okay, so I take moment, force, and perpendicular distance to the place where I take the moment. So it will be 0.4. So plus 0.5 g times with 0.4. Okay, alright, so I already got 2 clockwise. I've already put my value here. So if I solve this, okay, so this one will be 0.4 g plus with 0.2 g, okay, which will be 0.6 g. Okay, if you want to times with 9.81, you can go ahead. Okay, now I look at sum of anti-clockwise moment. Sum of anti-clockwise moment. Okay, so anti-clockwise is only this. So I'm going to take another color pen here. Okay, so this is the force. This is the part that I take moment. So perpendicular distance to the place I took the moment will be 0.2, 0.2, 0.2 is 0.6. Okay, so like this, you see, this one, anti-clockwise. Clockwise was this one, this one, this one, this one. Okay, so what do I get? R2, which I don't know what is it. R2 times with 0.222, 0.6. R2 times with 0.6. Okay, alright, so the concept says the sum of clockwise moment equals to sum of anti-clockwise moment. So if I write here, sum of clockwise moment is 0.6 g, sum of anti-clockwise moment is R2, 0.6. So R2 is equals to what? Is equals to g. So g is what? G is 9.81 Newton. Haven't finished yet, because the question asks us to find the reaction at A and P. Reaction refer to, they want us to find R1 at A will be R1, at P will be R2. Okay, so we haven't finished. So if R2 is 9.81 Newton, so we can use the first equation here. This is 9.81. So what is R1? Okay, equals to 2.5 times 9.81. So you can solve this. (14.7). So you get your answer for R1 is 14.7 Newton. So here is 14.7 Newton. Okay, so this is how you solve questions equilibrium of rigid bodies. Okay, all right, that's all.